All right, so today will be the fourth and last lecture of this lecture series on the index theorem. And we'll pull together the various strands that we talked about in the last three lectures. So let me remind you of sort of the highlights of these last three lectures. So in the first lecture, we talked about elliptic operators or differential operators. So let's say D is a differential operator from the sections of some vector bundle E into the sections of some vector bundle F. So this is a differential operator. And we talked about the principal symbol of such a differential operator. That principal symbol that we denote sigma of D was a vector bundle map between the pullbacks of the vector bundles E, F respectively, where these are vector bundles over the total space of the cotangent bundle of X, and the pi denotes the projection map from the total space of the cotangent bundle to X. And we talked about what it means for the differential operator to be elliptic, which means that the principal symbol is actually a vector bundle isomorphism away from the zero section of the cotangent bundle. Then in lecture 2, we formulated a particular version of the index theorem. Then there are sort of different versions of the index theorem out there. In lecture 2, we talked about the K-theory version, or K-theoretic version of the index theorem. That's a statement where we want to assume that our manifold X in question is closed and even dimensional, and that's a standard assumption. Our manifold X is closed and even dimensional. Then we showed that if D is elliptic, that implies that it has a well-defined index. So it's a Fredholm operator and has a well-defined index, which is an integer. And the statement of the index theorem at first is to say that this index does only depend on the principal symbol. So this does only depend on the principal symbol of D. More precisely, the principal symbol of D represents a K-theory element in the K-theory of the cotangent bundle relative to the complement of the zero section of the cotangent bundle, which I denote in this form. So since the ellipticity of the operator means that the symbol map is invertible outside the zero section, that is, it's invertible in here, this class, the symbol of D, represents an element in this relative K-theory group. And the index of the operator depends only on this K-theory class. In fact, a more precise statement is possible. Namely, there is a map from this relative K-theory group into the integers, which is defined purely topological. For that reason, it's called the topological index map, which has the nice property that this particular element in this relative K-theory group that's represented by the principal symbol of the operator gets mapped to the index of the operator. So we can calculate, in other words, the index of the operator in a purely topological way by first interpreting its principal symbol as an element of this relative K-theory group, and secondly, constructing this map by sort of homotopy theoretic means from this relative K-theory group to the integers. All right, so that was the main point of the lecture 2. So then lecture 3, we were focusing in on this relative K-theory group and trying to understand it in more explicit ways. And we proved the following proposition, that if X is spin, then we have a nice isomorphism. We have a different way to think of this relative K-theory group. Namely, there's a map from the K-theory of just the manifold X into the K-theory of this relative K-theory group, K-theory of the pair consisting of the cotangent bundle, comma, the non-zero vectors in the cotangent bundle. And this is the so-called Thom isomorphism. And is given very explicitly, namely, an element in the K-theory of this compact manifold X is represented by some complex vector bundle, say V. Under this map, this goes to the product of a particular class in here that's called the Thom class times the pullback of this vector bundle V to the total space of the cotangent bundle. And in fact, there's a nice analytic interpretation of this product. Namely, that turns out to be the symbol of the so-called twisted Dirac operator. So we constructed these operators in lecture 3, and we showed that the symbol of this twisted Dirac operator is exactly the class that correspond to the vector bundle V under the Thom isomorphism. So what we want to do today, so in the lecture today, is, well, it would be very desirable then to understand the composition of this map, this Thom isomorphism, with the topological index map, right? So we want to understand this, but more explicitly, right? I mean, both of these maps are have pretty intricate definitions, right? This is a Thom isomorphism, and this also was defined in terms of other Thom isomorphisms, and these are not easy to capture calculationally. So we want to understand the composition of these two maps, the Thom isomorphism here and the topological index map, in a more explicit form. And that's sort of what the goal is today. It's the following proposition. We want to understand this composition here of the Thom isomorphism. That gives us an isomorphism into this pair here, followed by the index map. Into the K-theory, into Z. Right? That's sort of what we really would like to understand in a more explicit way. So the question is, well, if you start with a vector bundle over V, then how do you calculate this number in an explicit way? The explicit way is this. You calculate a certain characteristic class known as the Chern character of this complex vector bundle V. So this is an element that lives in the even cohomology groups of the manifold X with rational coefficients. Then you multiply, and I'm going to go into detail about those things. That's the main thrust of today's lecture. Then you multiply it by another cohomology class, which is called the roof genus of the tangent bundle of X. That also lives in here. Then you multiply those things, you get again something in there. Well, then you have a cohomology class which you can evaluate on the fundamental class. So you evaluate this on the fundamental class of this manifold, right? It's even assumed to be spin, so that you have this Thom isomorphism here. And so then in particular it's oriented, so you have the fundamental class here which lives in the nth homology of X with z coefficients. To get a priori a rational number, since you're evaluating a rational cohomology class, but the theorem says no, this is in fact an integer and it describes this composition in an explicit way. Okay, so that is then as a corollary of this, you get a formula for the index of twisted Dirac operators, right? And that would be called the another version of the index theory, index theorem, namely the cohomological version. It says that, well, if you calculate the index of this twisted Dirac operator, right, by the abstract theorem here, it would be given by taking this class and mapping it under this composition. But now we have an explicit formula for this composition. So this is given by evaluating the roof genus, a roof class of the tangent bundle of X times the Chern character of V on the fundamental class of X. So that's very nice and explicit. So what I want to do today is not so much prove this proposition, but rather explain in detail what do those things mean and how do you calculate with them, and then hopefully I get around to doing explicit calculations for some four manifolds. So the proof of this is sort of standard for topologists by arguing that, well, sort of the Chern character as a map from K-theory to cohomology does not commute with Thom isomorphisms, but there is a fudge factor in there which is given by the roof genus. So if you know the story, hey, that's a proof of the proposition, but I don't want to dwell on that. Okay? So I want to first explain what are Chern classes. Okay? Well, it's the following thing. So if you have, I start with a complex vector bundle. Bundle V over some space X. So this is any topological space X. So this is not a closed manifold. Then you can produce Chern classes. The ith Chern class of this vector bundle V is in the 2ith cohomology of the base space X, coefficients in Z. That is called the ith Chern class. And then you can put all of these guys together to form what is called the total Chern class. And I write C of V, which is the sum of C0 of V plus C1 of V plus and so forth. And that is an element then in the even cohomology of X. And I want to now list the properties of these things here, of the Chern classes. So the first property is that the 0th Chern class, that's an element in the 0th cohomology, that's always the unit in the 0th cohomology. Secondly, the Chern classes are 0 in dimensions if the I is bigger than the dimension of the vector bundle that we talk about. So they peter out. Okay. Second property is you have naturality of these classes, by which I mean it's compatible with pullbacks. So suppose that you have a map F from a topological space Y and topological space X, and you have this vector bundle V over X, then you could first pull back the bundle and calculate an ith Chern class of that, or you can first take the ith Chern class of the bundle and then pull it back, and they are equal. The third property is an exponential property of the total Chern class. Namely, if you look at the total Chern class of a sum of two complex vector bundles, V and W, that's going to be the product of those two vector, of the total Chern classes of those two things. And the last property is a normalization property. So far you could satisfy these properties by just saying, well, it's always 0 except C0, which is 1. So you want to not say that. So you have the normalization property. To write down the normalization property, I want to say, what is the total Chern class of the line bundle over Cp infinity? So this is the tautological line bundle, also called the Hopf line bundle, which over each point of Cp infinity, which is a plane, which is a one-dimensional subspace of C infinity, attaches just that thing as a fiber. Okay? And then the condition is that if I take the first Chern class of this bundle, this lives in the second cohomology of Cp infinity. We know that the second cohomology of Cp infinity is isomorphic to Z. And this one here is a generator. And in fact, well, then there are two generators. So which generators of those two is it? Well, I can take it apart by saying, oh, let me write X for this thing here, by requiring that if I evaluate on the fundamental class of Cp1, right? That's a nice complex manifold. So the complex structure of this manifold picks out an orientation. If I evaluate on that, I want to get 1. All right, that's the normalization property of the Chern class. All right, so Chern classes are great, but they have a disadvantage. Namely, if you ever try to calculate the total Chern class of a tensor product of vector bundles, well, that's hard to calculate. You can do it, but it's algebraically a bad task. The only case that's easy is, suppose that L and L prime are line bundles. So L prime are line bundles. Then it's easy. So first off, then the tensor product is also a line bundle. Then the only interesting Chern class is the first Chern class. And the first Chern class of a tensor product is just the sum of these two first Chern classes. Well, that's easy. Well, what's the fix? So better properties with respect to tensor product is obtained, properties are obtained by looking at the Chern character CH of a vector bundle V. So this is an element, again, in the even cohomology of your space the bundle lives over. And the nice formal properties of that thing is that it's a ring homomorphism. So in other words, the sum, the Chern character of a sum of vector bundles is the sum of the Chern character of the summands, and the Chern character of a tensor product is the product of the Chern character. So couldn't be better. So this one here is just the sum of the Chern characters of the summands, and Chern character of a tensor product is the product of these cohomology classes. Okay, well, there's no free lunch. The price that you pay for it is, although the Chern classes are integer cohomology classes, these are only rational cohomology classes. So if you're a topologist, you care about the torsion and you don't want to throw away torsion. Here we need to throw away torsion in order to get these much more pleasant ways to calculate with that thing. Okay? So how is that defined? Construction. Of a Chern character. Comes in two steps. First of all, we're going to just think about, like, what should be the Chern character for a complex line bundle L. So L is a complex line bundle. Well, it should be built from the only Chern class that we have, which is the first Chern class. What you do is you take e to the first Chern class of L. What does that mean? Well, again, let me write x for the first Chern class of L. Then you're supposed to just write down the standard Taylor series for exponential functions. So you want 1 plus x squared over 2 plus x to the 3 divided by 3 factorial, and so forth. So where does this thing live? Well, it lives in the even cohomology of whatever your base space is. But you notice that you introduce denominators, so you are forced to take rational cohomology. And you also notice that this thing might not live in the direct sum of cohomology groups. It lives in the direct product. So by this, strictly speaking, I mean the product of all the even cohomology classes of X with rational coefficients rather than the sum of those things. Right? So that's it for a line bundle. How do you get it for a general bundle? Well, let's assume first we want to apply it to the special case where the V is the sum of line bundles. Ln. So LI's are line bundles. And let me denote the first Chern class of these line bundles by xi. Okay, so then we want to make sense of what is the Chern character V. Well, for a sum, it's supposed to be the sum of these things. So in other words, this is the Chern character of L1 plus the Chern character of L2 ... plus the Chern character of Ln. Right? Now, each of these we already know what they are, right? They are e to the x1 and so forth, e to the x1 plus e to the xn. All right. So we also know how to write it down for vector bundles that happen to be sum of line bundles. The question is, well, what do you do in general? And there's sort of two ways to argue. One is to argue with the so-called splitting principle, but I'm going to argue using elementary symmetric functions. So there's two ways to go here. So let me contemplate for a moment what the Chern class of V would look like. So what is the total Chern class of V? Well, on one hand, the total Chern class is defined to be 1 plus the first Chern class of V plus the second Chern class of V, up to the top dimensional Chern class, which for this n-dimensional vector bundle would be the n Chern class, and then it's 0 from there on, right? On the other hand, I know that the Chern class of a sum of bundles is given by the product of the total Chern classes of these things. So this is C of L1 times C of L2 times C of Ln. So for each line bundle, what does the total Chern class look like? Well, it always starts out with 1, any total Chern class. And then there's C1 of that bundle. So that's what we called X1 there. But there are no higher terms, right, since it's a line bundle. So this is it for the total Chern class of the line bundle L1. Similar for the other stuff. So this is the total Chern class of the line bundle L2, and so forth. Oh, then I can multiply those things out, right? I multiply those things out, I get 1 plus, and then the next term is sort of the sum of all of these xi's. And then the higher terms, slightly more complicated to write down, and then the very highest degree term would be the product of all the xi's, right? X1 times xn. Then you might recognize those things, right? These are called the elementary symmetric functions in these variables xi. So this is the so-called first elementary symmetric function. And then comes the second one that I didn't write down. I was lazy. And this is the nth elementary symmetric functions. So these are elementary symmetric functions. In the xi's. So what do I see by comparing this side with that side? Oh, I see that the ith elementary symmetric function is just the ith Chern class of V, right? Now I go back here. Notice this thing here is symmetric. Symmetric in the xi's. Right? Nothing happened if I permute those things. What does that mean? Well, then I can use sort of this algebra theorem saying, oh, if I have a function which is sort of polynomial in these things, so you might argue, oh, but it's not polynomial. Well, zoom into whatever homogeneous part of it, that's a polynomial in the xi, and well, it must be a symmetric polynomial in the xi's, and hence you can express it in terms of the elementary symmetric things, which are just the Chern classes of V. So hence, this is a function of, well, the Chern classes of my original bundle. So I didn't need to assume that this is a sum of line bundles. No. I get once and for all a formula in terms of the Chern classes of the bundle. So that's my definition then of the Chern character. Okay, everybody good with that? All right. So that explains the Chern character. Now we need to look at the other piece. We need to look at the Aroof genus. And if you remember, the Aroof genus was something that we applied to the tangent bundle. So unlike this vector bundle V that we twist by, the tangent bundle is a real vector bundle. So now we want to look at characteristic classes for a real vector bundle. bundle, say E over X. Okay. So how can you make interesting characteristic classes out of that? Here's the definition. You do sort of a dumb thing. You say, well, if I have a real vector bundle, then I can also complexify it to get a complex vector bundle, right? You complexify it. That's a complex vector bundle. And then you can do all whatever you constructed before, you can apply to that complex vector bundle. So for example, you could take the 2ith Chern class, the ith Chern class, the 2ith Chern class of this. And this is a new class, which with a minus sign is called the ith Pontryagin class of E. And so that's in the same dimension of the 2ith Chern class that will live in dimension 4i. So that's an element in the 4ith cohomology of X. It's called the ith Pontryagin class. Oh yeah, minus 1, yes, minus 1 to the I, thank you. Ith Pontryagin class. And yeah, you can also then define the total Pontryagin class. It's called P of E. Sort of by saying, oh, you take 1 plus the first Pontryagin class of E plus the second Pontryagin class of E, and so forth. Right? So you might wonder, well, what about, why is there this funny minus sign involved in there? Well, it just, to make calculating with the Pontryagin class is nicer. So to show you that the minus sign there helps, let me calculate what the Pontryagin class is for, let me calculate what the Pontryagin class is, the first Pontryagin class is for a line bundle. So L is a complex line bundle. So by definition, this is the second Chern class, but with a minus sign of the complexification of this line bundle. And if you think about the complexification of a line bundle, well, that's sort of that line bundle plus its dual, right? So it's minus second Chern class of L plus its dual thing. So to calculate the second Chern class of it, oh, it may be easier if you write down what is the total Chern class of L plus L bar. Oh, by the exponential property of the total Chern class is the total Chern class of L times the total Chern class of L bar. What's the total Chern class of L? That's 1 plus the first Chern class of L. What's the Chern class of L bar? Well, it's 1. The first Chern class of the complex conjugate is minus first Chern class of the original bundle. You get this one. So as you multiply it out, you can see this is 1 minus, and you see that the even thing, that the first Chern class of this bundle is going to be 0. And you get this thing here. So that's the secret reason that we skipped sort of the odd Chern classes of the complexification. They turn out to be just two torsion classes, so we don't want them. Okay, so in particular then, the second Chern class here is minus the first Chern class squared. So this minus sign helps to just say, oh, well, this is the square of the first Chern class of the vector bundle that I'm looking at. That sort of makes it more pleasant. Okay, so just see, I don't forget anything. Okay. Yeah, now I want to again look at what is the total Pontryagin class of a sum of complex line bundles. So the Li are complex line bundles. Okay. So we have the exponential property, that's the Pontryagin class of the first line bundle times and so forth up to the Pontryagin class of the last line bundle. What does the Pontryagin class of this line bundle look like? Well, according to this calculation, it's just 1 plus the square of the first Chern class. So as before, let me write xi for the first Chern class of the line bundle Li, and so forth. 1 plus x n squared. So you can multiply those out again. What do you get? Well, you get 1 plus, and then you get x1 squared plus da 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 da, xn squared, plus and so forth. Let me write down the highest term, which is the product of all of these things. It's x1 squared, xn squared. Oh, so again, we see that the elementary symmetric functions come up, but this time not of the xi's, but the squares of these things. So this is sigma 1, and this is sigma n, the elementary symmetric functions in the xi's in the squares of these things. So now we want to build so-called exponential characteristic classes. So I want to look at a set of exponential characteristic classes Q for real line bundles E. Vector bundles. And they are supposed to live in, the cohomology, the even cohomology of the underlying space with rational coefficients. And the exponential property means that, as you saw in the Chern classes or Pontryagin classes, that if you apply that to a sum of real vector bundles, that should give you the product of these things. Okay? So our Eruv genus will be one of those things. Now, this Eruv genus was built by Hirzebruch, who built a whole machine by constructing, so this is Hirzebruch's construction. I need to mention his name, this is my academic grandfather. Construction. And what he starts with is a power series that I call little q of x, which starts with 1. And it's an even power series, so there's no linear term. There's the first term involving an x squared, no tertiary term. It's like that. So it's look at power series like that. So for each such power series, you want to produce a class here. So how do you do that? So this little q goes into capital Q of E. I need to define what this is. I'm going, like as I did in the case of the Chern character, I'm first going to tell you what this is for line bundles, and then I'm going to argue from there. So Q for a line bundle L. So now I apply this to a complex line bundle. Well, that's going to be just this power series Q of x, where now I think of x as being the first Chern class of this line bundle. right? That makes sense. And then this one here is an element in the even cohomology of X with rational coefficients. Oh, I should have said the AI here I'm thinking of as rational numbers. So I end up with cohomology class with rational coefficients, right? Okay, so how do I do it for a vector bundle V, which is a sum of things? Sorry, vector bundle E, which is a sum of these things. Well, it's supposed to be multiplicative, so that better be this one here, the product of Q applied to each of these line bundles, right? But Q of each of these line bundles, we already know what it is, maybe by this assumption. So this one here would be the power series applied to x1 times ... the power series applied to xn, where xi, as before, is the first Chern class of the ith line bundle, right? Now, this one here, what kind of function in the xi is it? Well, it's a symmetric function of, well, since this is an even power series, it will always be expressed in terms of the squares of xi, right? Xi squared. Oh, but if it's symmetric, then it can be expressed as a function of the elementary symmetric functions of the xi squares. But, oh, these were the Pontryagin classes of the bundle we started with, right? So, hence, function of the elementary symmetric functions in these, which is the ith Pontryagin class of the original bundle. Okay? All right. So now we defined most of what we need to do the calculation, to define the A-roof genus, and hence to define the right-hand side in the proposition that I wrote down. So now this A-roof class in here for a real vector bundle, that's an element in the cohomology of X with rational coefficient. That's the class that under this construction, or I should say, this is actually a bijection. So any such class comes from uniquely from such a power series. And this A-roof class, that corresponds to a power series, denote this way, which is the power series belonging to, I'm always a little confused about what is in the denominator and what's the numerator, but I think this is right, and I'll check this in a second. X over 2 divided by the sine of, hyperbolic sine of x over 2. And you can convince yourself this is in fact an even power series, right? Weird, right? So let me write down the first coefficients, which you can do by Taylor expansion. So this is equal to 1 minus 1 over 24 times x squared plus, then the next term is x to the fourth. And it's good to sort of write it in terms of prime factor decomposition, this rational number that's in front of it. So it's 2 to the 7 times 3 squared times 5. So it has very interesting denominators here. Okay, so that explains, that makes clear what all the terms in this proposition mean. Now let me write down a corollary. So let me apply this proposition that we wrote down to four-dimensional manifolds. So if X is a spin 4 manifold, we want to figure out what is the index of its Dirac operator, right? According to the general proposition that says, well, you just take the A-roofed class of the tangent bundle of this manifold, and evaluate it on the fundamental class of this manifold. But now we can be more explicit, right? What is that a roof thing here? Oh, and that's something I should have written down before. Maybe I'll write it down here. Let me deduce from this the following. So suppose that you want the roof genus. Let me just say it. So that implies that the roof genus of any vector bundle E is equal to 1 minus, and this term is a 4-dimensional term. So it will only depend on the first Pontryagin class of this bundle. And which multiple of the first Pontryagin class it is, well, you can check by just plugging a line bundle. So that multiple is minus 1 over 24. So that is saying the roof genus of E is equal to 1 minus 1 over 24 times the first Pontryagin class of E plus higher terms. Okay? So then you can say, okay, well, plugging that in, the only relevant term for a 4-manifold is this 4-dimensional class evaluated on the fundamental class. So we get this is equal to 1 over 24 times the first Pontryagin class of E of the tangent bundle of the manifold X evaluated on the fundamental class. So in other words, if you know the first Pontryagin class of your manifold and you can evaluate it on the fundamental class of that thing, you're good to go, and you calculate what the index of the Dirac operator on this is. So in the last 10 minutes, I want to apply that and to do very concrete calculations with 4-dimensional manifolds. So some calculations of the first Pontryagin class of, let's write it like this. For 4 manifolds. Okay, the first example is going to be the complex projective plane. The first thing you need to know is you need to know what's the tangent bundle of that. For me, it's easy actually to generalize that by saying, well, there's a case of a Grassmannian, right? If you have a Grassmannian of k-planes in complex k plus n space, what is the tangent bundle of that? Now, over this Grassmannian, you have sort of 2 tautological bundles, right? Namely, a point in here is a k-dimensional subspace of ck plus n. Well, all the vectors in that k-dimensional subspace, they form a tautological k-dimensional bundle. Or you can take the orthogonal complement of that. That's a tautological n-dimensional bundle. And the tangent bundle turns out to be isomorphic to the homomorphism bundle of the tautological bundle into its orthogonal complement. So this is the tautological k-dimensional bundle, and this is the tautological n-dimensional bundle. So in particular, let's apply that to CP2. And you see, oh, this is hom from the tautological 1-dimensional bundle into the tautological 2-dimensional bundle of that, right? So how do you calculate that stuff? Well, it's actually not hard. Here's a trick. You add to that a trivial line bundle, complex trivial line bundle. But you think of this complex trivial line bundle as the identity, as a homomorphism bundle from gamma into itself, right? That has a tautological section, namely the identity, so it's a trivial bundle. But then you can put these things together, get hom of gamma into gamma perp plus gamma. But hey, gamma perp plus gamma is adding to the trivial bundle of dimension 3 over this complex projective plane. So this is the trivial 3-dimensional bundle. Oh, so that means you have 3 copies of the homomorphism bundle from gamma into the trivial 1-dimensional bundle. And this thing we call the dual bundle, right? So what I'm saying is, oh, if you allow yourself to add a trivial line bundle, the tangent bundle just becomes the direct sum of 3 copies of this dual tautological bundle. Okay. So what does that mean then for the first Mondragon class? For the first Chern class? What do I want to know? I want to maybe do the first Mondragon class of this thing here. So the first Mondragon class doesn't change if I add a line bundle to it. So that's the same thing as a first Mondragon class of 3 copies of the dual line bundle. Well, what is a Mondragon class of a direct sum of 3 things? Well, that is 3 times the first Mondragon class. What is the first Mondragon class of this line bundle? Well, it's the square of the first Chern class of that. The first Chern class of gamma was our generator in the cohomology of CP infinity. So the first Chern class of that is minus that, but I squared it anyway to get the first Mondragon class. So this is 3 times x squared, where x is sort of the usual generator of second cohomology of CP infinity, which then restricts down to generator of CP2. So what is that saying? Maybe I should write over on this side now. What is that saying for the A-roof genus? That is the evaluation of the A-roof class on the fundamental class. Well, the A-roof class was minus 1 over 24 times the first Mondragon class, and the first Mondragon class of that we calculated to be 3 times x squared evaluated on the fundamental class of CP2. Well, x squared evaluates to 1 on this one here, so this is minus 3 over 24. It's minus 1 over 8. Sounds surprising, right? Since it's supposed to be the index of the Dirac operator. So what did we do wrong here? Exactly, very good. No problem. It's the question was the answer was, well, you know, this is not a spin manifold, so therefore we don't have a Dirac operator. So therefore there is no reason why this thing is supposed to be an integer. This is correct. So CP2, not spin. Okay, so this was sort of an unfair example since, well, it's really supposed to be more interesting for spin manifolds. So let's do a final example, namely a 4-dimensional spin manifold. I want to talk about the Koomer surface. That's my second example. Koomer surface. Okay, that is a subthing of the 3-dimensional complex projective space consisting of points Z0 through Z3 in the 3-dimensional complex projective space, which satisfy a quartic equation. Namely, if you take the 4th power of all the coordinates, that's supposed to give you 0. So this includes, well, inclusion map I call I, into CP3. Okay, so first thing is we need to figure out, well, what's the tangent bundle of that thing, right? What do we know about that? Well, it embeds in CP3. So if I add to the tangent bundle the normal bundle, the normal bundle. Then I get the tangent bundle of the ambient space restricted to K, right? So I get the tangent bundle of CP3 restricted to K, or in other words, pulled back via inclusion map. So now I need to identify these pieces here. What is this? Well, what I did over there for CP2 works equally well for this one here. So this up to stabilization is really the tangent bundle of this one here, up to adding a line bundle, a trivial line bundle, is just 4 copies of the dual of gamma. What is this normal bundle here? Well, this, the left-hand side of this equation you can interpret as a section of the 4th power of the bundle gamma star over CP3. So that way you can then think of K as the 0 section, the zero set of that section. So therefore the normal bundle is exactly that bundle restricted to K. So this one here is just the restriction to K of the 4th power of that one here, right? So what does that say for the first Pontryagin class of tangent bundle of K? Well, it's that. So it's the first Pontryagin class of that thing here, which is a 4th Pontryagin class of 4 times gamma star. And then I need to bring this on the other side, so I get a minus sign here, minus the pullback of the first Pontryagin class of that thing here to the power 4. Okay, what is this stuff? Well, let's see. So the first Pontryagin class is always the square of the first Chern class of the stuff in question, right? So squared. What is the first Chern class of a 4th power? Well, that's 4 times the first Chern class of whatever. And then we need to square that. Okay, so that gives us 16 times minus x squared, which is same as x squared. Pretty good with that? So what is this here? Well, it's just 4 times first Pontryagin class of gamma star. And this is just x squared, so you get 4 times x squared here. Okay, what's the total? Well, we get 4x squared minus 16x squared. So it's I star of minus 12x squared, right? All right, so now let's finish this up. So what is the roof class of the tangent bundle of the Koomer surface evaluated on the fundamental class of the Koomer surface then? Well, we know by our general index theorem that is minus 1 over 24 times this class evaluated on the fundamental class. This class is, what is it, minus 12. So let me pull out the minus 12. So 2 minus signs cancel each other, and I get a 12, 24. So I get 1/2 times, and then I have I star of x squared evaluated of the fundamental class. And then you go like, isn't the 1/2 bad news for things here? But no. You need to evaluate not on the fundamental class of CP2, you need to evaluate on the fundamental class of K. So what you need to do is you need to bring this thing on the other side. You need to evaluate I star on the image of the fundamental class of the Koomer surface in there. Right, the Koomer surface is embedded in CP3, but since the Koomer surface is 4-dimensional, you can push it down the map and you end up in the fourth skeleton of CP3, which is CP2. So then that way you get a map from K into CP2 of manifolds of the same dimension. But the question is, what is the degree involved? Well, the degree is exactly the degree of the polynomial that defined the Koomer surface, which is 4. So therefore, hey, this thing here is 4 times fundamental class of CP2. We know that x squares evaluates there to 1, so you get 2. So everything is good. No, it's in fact an integer. In fact, it's an even integer. So the index of the Dirac operator on this Koomer surface is 2. Thank you. Any questions?
Is it possible to get 1?
The question is it possible to get 1? The answer is no. The reason is that if you look at the Dirac operator in 4 dimensionals, it turns out that it has a quaternionic structure. So as a complex vector space, it is always even dimensional, the kernel and co-kernel. So therefore, no, that's the smallest one you can get.
Rockling's theorem is somewhere around here.
See,
Rockling's theorem.
exactly. So one way of proving Rochling's theorem is to say, yeah, you can express this signature in the same way as the index of the Dirac operator, since also the signature is the index of an operator, so-called signature operator. And that turns out to be a different multiple of P1 evaluated on the fundamental class. But then, since you know that the smallest multiple that you can get sort of from the A-roof genus is that tells you that the smallest signature you can get is always divisible by 16. So that's a consequence of these calculations. All right, thanks.